Okay, so yeah, we're very happy to have Praxitelis all the way from Scotland, who is going to talk to us today about black hole superpotential as a unifying entropy function and BPS thermodynamics.
Thank you, Laura, both for organizing my visit. Thank you all for hosting me. So yeah, I'm going to talk about this title here. It's a project that I did with Yannis Papadimitriou, who's recently joined the University of Athens as faculty. And also I'm going to say a few words about some related work with Euclidean and Sergei Ntokos from the University of Edinburgh. How should I?
Is it working?
With the standard arrows, no.
You may need to click on
the
screen.
Okay. Okay, so in the broader sense, the problem is about deriving microscopically the entropy of black holes in ADS. And since ADS CFT, we know how to do that. We know what we should do actually. In principle, count states on the dual free theory. And for ADS3, that's relatively simple. I mean, we know that we have a CFT, a two-dimensional CFT, infinite symmetry algebra, we have a Carty formula, so we can derive the entropy. In higher dimensional problem, it's much harder, and as shows this 20 years gap here in this history, almost 20 years gap, you need to use different techniques for a weaker problem for supersymmetric black holes. So for this talk, I'm going to concentrate in ADS5 black holes, but many of the things I'm going to say and the approach I'm going to describe is more general. So in the beginning, just I will say a few words about black holes in ADS5, just to give the setup, to introduce the setup, and also to explain the motivation behind our approach. Then I'm going to describe our approach in the most general form possible. Just a disclaimer here: when I use the word superpotential, it doesn't necessarily mean it has to do something with supersymmetry. It's in the sense of superspace of the Euclidean. When I want to talk about superpotentials related to supersymmetry, I will use the term BPS superpotentials, just as a disclaimer, which will be the last section of my talk. So please interrupt me with questions and everything. So the context, the theory I had in mind was gauge supergravity in 5 dimensions with 3 gauge fields, 3 abelian gauge fields. I will give more details on that later. So typically black holes in this setup have 6 conserved charges. Because they are stationary, they have their energy, 2 angular momenta, because you have 2 Killing directions, angular Killing directions, and 1 electric charge for each U1 gauge group. So there are some solutions that are very complicated in this theory. They were found about 11 years ago in a very hard to read paper by Wu. You can look for, yeah.
What's the decomposition and CAS plus E?
Okay, this is the Casimir part.
This part.
This one.
Yeah. Oh,
Casimir part. Yeah, I can discuss more about it. Yeah. So yeah, I mean, when you can find similar solutions by identifying the 3 U1s there, you can find the solution to the minimal gauge supergravity theory. And you could only go even turn off completely the electric charges and discuss the ADS5 black hole. But we are interested in supersymmetric black holes. And it turns out, I mean, this you all know, I guess, the BPS relation that this black hole should satisfy, the energy is completely determined by the other charges. A less well-known constraint for BPS black holes is that they satisfy also a non-linear constraint among the charges, which has this polynomial but yeah, complicated form here. So this is induced by 2 the parameters of the regular black holes. And
why does this function?
okay, so I have 2 answers. First, you can check it on the solutions that they are regular because of this. I have another answer that I want to give in the end. It also comes from regularity conditions correction. But I would like to give that answer later because it comes very elegantly in the formats I'm going to describe. But you can play a bit with this and you can see that BPS black holes in 5 dimensions have to be both rotating and charged. So you cannot go to a simpler setup to discuss the phenomenon you want to discuss. There is one thing you can do. You can take the two angular moments to be equal, and this results in a sector of the theory which is SV2 cross U1 invariant, and things are simpler in this setup. And this is the setup, the sector I'm going to focus on. Okay, before moving on describing, so are there more solutions? I mean, these are the known ones. All of the solutions I told you about, I didn't give them explicitly, but I was talking about asymptote approach ADS asymptote, global ADS asymptote. So they have a standard form. So one may ask, are there toric solutions with more general asymptotics, local ADS, spherical local ADS? And there are some solidons in the theory, but since we are interested in entropy equations to compute and to explain the entropy, we are very interested in solidons, the horizon. There are also numerical solutions for black holes that have been constructed with these more general asymptotics, but it has been realized recently that these do not have smooth horizons. So it's not exactly clear what's the role of those solutions, at least holographically.
How are the horizons not smooth? Is it due to like cusp, or what kind of non-smoothness is it?
Of the horizon also.
When you say these do not have smooth horizons, what sort of non-smoothness is that?
Oh, okay. So they have the metric is not C2 differential, it's C1.
Okay.
So you have divergences. Okay. So one may wonder if we can classify all the solutions in this theory. And one can say a few things. For example, it's an old result that every solution, every black hole solution, actually every solution, supersymmetric solution, can have this form, and all the data can be determined in terms of some Kähler surface. Here, I don't give all the conditions, but and even the Kähler surface is not arbitrary. You don't choose an arbitrary. It has to satisfy a complicated fourth order nonlinear partial differential equation for its Kerr function. So solving it in general, it's quite hard. Even with for toric solutions, it's hard. You can do some assumptions. You can say that it's of Calabi type. I don't want to get too much into the details of the technical details of this. And then you can prove a uniqueness result actually for these black holes, a uniqueness theorem. So for every smooth and compact horizon, especially compact horizon, you can show that the solutions I told you about in the minimal theory is the only one, or it's near horizon geometry. There are some here. I mean, this theorem does not assume anything on the asymptotics, which is in contrast to, for example, the non-Kerr theorems. Assume that you have some asymptotics. It covers the SU2 plus U1 sector. And we are working on generalizing this theorem when you have scalars, in a more general case supergravity. But the moral of this, what I want to say, is that all these techniques are very special to the theory you consider, so it's not very clear how to apply the general dimensions. So for the rest of the talk, I will be agnostic to such results. It's really hard to chart the full space of solutions in this theory. Okay, whatever the solution is, for large charges, I should be able to compute the entropy from the dual field theory. So from the degeneracy of the states. And the right object to compute is the grand canonical partition function in the BPS sector. And this is that for large charges, you can see from this formula here that in order to derive the degeneracy, you have to invert this relation, so it's a Fourier transform. And for large charges, you do a saddle point approximation. And then the extreme is produced together, should be produced. The extremisation is with respect to the chemical potentials. Well, I said the partition function typically compute the index. That's the easy compute, and you have some arguments to why they are the same in some setups. But I don't want to get into many details for that. But just to be concrete, in ADS5, the relevant quantity to extremize was conjectured by Zaffaroni and collaborators about 5 years ago, and it has this form. So it's the ratio of the chemical potentials for the electric charges over the angular momentum, of the chemical potential for the angular momentum. And you have to extremize that with respect to the chemical potentials, but subject to a constraint, which has this form. And when you do that, you really get the entropy of the non-black hole solutions, the correct value.
Go ahead. Go ahead.
Yeah.
As far as yeah, I can see the chemical potentials are complex or something like that.
Yeah, they should be, these chemical potentials should be complex. Hmm?
Yeah.
That gives the right answer. Yeah, but we will come back to that later. But at that point, that was just a conjecture. I mean, motivated conjecture, but yeah.
Yeah, I just so in this boxed equation, the first term is the log of the partition function, right?
Yeah.
So this conjecture about the form of the dependence of the log of the partition function for these theories on the charges, where does it come from? Or sorry, the chemical potentials, where
This form. So they had computed, it was computed a few years earlier, the supersymmetric asymmetric energy of these backgrounds, and they found that it has this value. But at that point, it was not clear what the Casimir energy has to do with the degeneration of the ground states. So the conjecture, they said they gives the right value. You can do bulk computation to compute the partition function.
you have evidence that this conjecture actually works. So
Yeah. Okay. And I mean, okay, in the field theory, there has been a lot of progress. It has started very early with work of Mark and other people, but there has been very recently, I don't cite everyone here, because there are too many, and also because I'm not so much interested in this talk in the field theory part of, but what we wanted to understand is how this extremization principle works on the path. In particular, what do we extremize? In which space group of solution of configurations do we move in order to extremize? So we want to derive that from first principles. So we wanted to go slightly off shell there, and without resorting to the explicit form of solutions. So when you have a solution, typically people write the regularity conditions. So I mean, it's built in. So we wanted to see to disentangle the regularity from the problem. And also, I mean, it is well known for many years ago, there's another extremization principle for with extremal black holes, not necessarily supersymmetric sense extremization. And we wanted to see how these two were related. So to do so, we formulate the problem in terms of an effective superpotential, which I will go into details now. As an aside motivation, we also want to see how the BPS relation is modified when you have more weird asymptotics like statistical law. Okay, any questions? Okay. So now we'll set the formal instructions. So this formal notation in this form I'm going to present works when you have a supergravity sector that the dynamics is effectively one-dimensional in terms of some radial problem. So the prototypical example you can have in mind is just black holes, static black holes in equal 4 dimensions. So in this answer, you can see that you have a so-called radial lapse function in analogy with EDM formalism. Some blackening factors, some effective size of the transfer space, which you can think of as a sphere, some magnetic charges. So, okay, in that case, you already understand that the problem is one-dimensional, effectively. But also there are sectors, I mean, with for rotating black holes, for example, that effectively the problem is one-dimensional, even though it's not obvious from the very beginning. For that is the case, for example, in 5 dimensions, that you have 2 equal angular momentum. And you can have some squashing parameters that describe the formations of the internal geometry and effective size and and scalar fields. something that will be important is that this function, the Lagrange function, is not a dynamical degree of freedom, it's a Lagrange multiplier actually, because it's describes the reparameterization of the radial coordinate. So, okay, I make my typical supergravity action with my metric and a bunch of scalars and one gauge fields. Many of the things I'm going to say also apply to flat space, but I'm primarily interested in ADS black holes, so I'm going to assume that the scalar potential is negative at the critical value. And you reduce the action to the RT plane, and you get up to boundary terms a one-dimensional Lagrange. Okay, I'm cheating a bit here. There are some Chern-Simons that are not very important, but the important thing is that the Lagrange, the way the Laplace function enters the Lagrange in the kinetic and the potential term. And if you compute the Hamiltonian for that, you get that it's proportional to the Laplace function, so the Hamiltonian vanishes. Well, that's a textbook example. I don't know if undergrad or grad. I mean, when you have reparameterization variance, the concept of energy vanishes, the Hamiltonian. So, in the Hamiltonian, just a short reminder of what the Hamiltonian performance means. You write the momenta, your theory, as gradients of a function of all the fields. And this Hamiltonian constraint then becomes a partial differential equation. And what you have achieved is to split the equations of motion, the second order equations of motion in two sets. One partial differential equation, the Hamilton-Jacobi equation, and some other, which are the definition of moment action, which are first order flow equations. This formulation is very natural from a holographic perspective, because half of the integration constants coming from the Hamilton-Jacobi equation describe actually the waves in the normalizable modes. It's what Charles, even here it's written, was saying in his lecture before, so he had a split of the functions. The other are describing the sources, the other half integration constants. Any question? Okay, that was very generic. You can exploit the symmetries of the problem, and you can find just method procedure that you have that the momenta for the angular velocity and the electric field are actually conserved along the radial flow. So in that case, when you have such conserved charges, you can reduce the form of the Hamilton-Jacobi function. I mean, the fields appear, the corresponding fields appear trivially in the Hamilton-Jacobi expression. And you have another symmetry, which does not result in a conserved charge, it's the time rescaling from a higher dimension point of view, which tells you that the blackening factor should appear as an overall factor in the Hamilton-Jacobi function. The object that remains that encodes the non-trivial dynamics of the problem is what we call the superpotential. So it's the non-trivial part of the Hamilton-Jacobi function. So the Hamilton-Jacobi equation becomes a partial differential equation for the superpotential, and also the flow equations become first order flow equations for the superpotential. So how does it work? If you tell me that you found the solution of the Hamilton-Jacobi equation, so you find the superpotential, you can then solve this coupled system, and for the trivial functions, the electric functions that are related to the conserved charges and the blackening factor, you can just integrate them to find the solution. Okay, too abstract, probably. So let's look at a simple example. So let's take the simplest case, just Einstein-Maxwell theory, ADS, which is a cosmological constant, and consider that it's static. And so the only non-trivial variable there is the effective size of this plasma sphere, actually. And you have the electric component as well, but this you can integrate it afterwards. So then the Hamilton-Jacobi equation is not a partial differential equation, it's an ordinary one, and you can solve it, and that's the solution here. From the solution, you have an integration constant, and consistently with what the general formula is, this integration constant actually corresponds to a normalized mode, mass. So, and this is, of course, a charge in dual field theory. That's very simple, and in the standard gauge that the effective size becomes the actual radial coordinate. If you pick, you get the standard form of the Rising-Hristov solution. A less trivial example, it's about extremal black holes. So the near horizon geometry of extremal black holes. Then you exploit this, you know that the solution there should have an ADS2 throat times some sphere or so. Yeah. And all the solution in the near horizon region can be parameterized in terms of some constants, which are undetermined, which are effectively the size of ADS2 throat, the size of the transverse sphere at the horizon, and the other variables. In order to determine those constants, you plug them into the equations of motion and theory, and we can determine. But there is a more elegant way to cast it. Most of this is related to sense formalism. So what you do there is you integrate the Lagrangian and the near horizon region over the transverse sphere, and you take the Lagrangian transform. You take the Lagrangian transform so up to a boundary term, which is important actually, but it's related to the 1D Hamiltonian. And the recipe, the prescription by Sen says that you should extremize this function with respect to the variables it has. And so this you can find the solution in terms of the charges. And at its extreme, it gives the entropy. In our formalism, the sense entropy function is related to the superpotential by this formula here. So, okay, so back to whatever I said is without having horizons. I mean, not without having horizons, I didn't assume any horizon. When you have an horizon, from the flow equations, and assuming that there are some smoothness conditions, you know the behavior of the fields close to the horizon, you can determine the near horizon behavior of the superpotential. And from that, you derive that the conditions are these ones. So the superpotential is extremized with respect to every variable except perhaps the radial size of the sphere. And this is related to the temperature times the entropy. This is the extremization conditions. I mean, extremization, I mean, of course, here it's not extremized, it vanishes, but okay, allow me this terminology. And for extremal black holes, you actually get sense extremization principle. But this is more generic, so I would like to use that as a generalization of sense extremization, even for non-extremal black holes. With the superpotential, you can also analyze the thermodynamics, which is actually a very useful thing, without knowing the full solution. So, if you do proper holographic analysis and the holographic normalization and deriving the word identity, I don't want to get too much into the details of that, but you can see that the charge that you copy holographically, the word identity, actually coincide with the charges that are radially conserved.
Yeah, can we go outside by separate question? Just to make sure I follow the logic. Yeah, so the superpotential is basically the solution to the Hamilton-Jacobi equation. Okay. Now the point that you're making here, so but knowing this superpotential is not equivalent to constructing a precise solution.
No, you have to show that.
Yeah, so or you have to solve the second set of equations for the game. So the point here you're making is that you can get all you need in order to extract the thermodynamics of the solution with fixed charges asymptotically is the solution to the superpotential. Plus this extremization principle. Is this the point that you don't?
Well, depending on what you mean by thermodynamics, it's generic thermodynamics or the special kind of thermodynamics.
I'm not sure I understand what
Well, if you want to describe it, you have to repeat the entropy. Yeah, you can do it without.
right. So the entropy you can extract it with solving only the Hamilton-Jacobi without actually constructing the explicit solution.
Yes, and imposing the energy. As in sense, spirit. Okay. Since you're talking about thermodynamics, you can, I mean, what people do typically is that they have the solution, they compute all the thermodynamic quantities, and they say, oh, we have that the quantity-statistical relation satisfied, the first law is satisfied. With a superpotential, you can do that without having the solution. So, because actually, what is the superpotential for the Hamilton-Jacobi function is actually the Onsen action. So, for example, relations like the quantity-statistical relation that relates the Euclidean Onsen action, the renormalized one with the Gibbs free energy, are given guaranteed. It's a little bit important too. And also the first law, because we have emulated the problem in a Dirichlet way, in a proper holographic way. Yeah. So now I'm going to move to the, the BPS case would, we can say more concrete things. Are there questions? Okay. Okay, so a valid objection is that you can say, hey, that's a really reformulation. You can move the difficulty of solving the equation of motion, just the difficulty of solving the Hamilton-Jacobi equation. Maybe it's even more difficult. There are, however, cases that you can solve the Hamilton-Jacobi equation, without too much hassle. And one of these cases is supersymmetry. So when you have supersymmetry, you have a killing spinor equation in the bound. You have that the variations of the fermions vanish. These equations, okay, so how does this work? The spinor should preserve, parameter is how much supersymmetry you preserve, so it has to satisfy some projection equations. If you have a large enough symmetry, the spinor should depend non-trivially only on the radial coordinate. This is part of the definition of you having a one-dimensional problem. And the important thing is that the killing spinor equations contain only first derivatives. But recall also that the flow equations have first derivatives. So by combining the components of the killing spinor equation, you can derive a relation of this form. And recall that one of the flow equations has this form. So you can identify this piece in the killing spinor equation with a superpotential. And you have a solution of the Hamilton-Jacobi equation. You can plug it in and do it. So you can find that. Note that in this process, you didn't assume any horizon. This describes every supersymmetric solution, no regularity condition, and describes also solid holes and irregular black holes because the local condition. Okay, how does this work now in concrete examples? So perhaps the toy model, let's say, or the one that was derived earlier, is the four-dimensional case. So there, the STU model, the so-called, has a gravity multiplet with a magnetic anti-gravity photon and three vector multiplets, three gauge fields and three complex scalars. Typically, it's better to write this in terms of some constrained scalars. So four independent constrained scalars, which are called holomorphic sections. And the theory is determined by supersymmetric data, prepotential, the current potential, and superpotential. And black holes in this theory, I don't have to say that, but are uplift in M theory solutions with AGS 4+7 asymptotes, which we know that they are dual to ABJM theory with checksum level 1. And the black hole entropy is expected to scale like 1/G Newton, which in the case of ADS 4 CFT3 scales like n 3/2. So black holes in this theory, or static dionic black holes in this theory, are described by these subsets that I showed you in the beginning. And the superpotential in that case has been derived long ago by the Daniaki and has this form here. It's in the terms of the supersymmetric data of the theory, the superpotential and the prepotential. This formula here. And in fact, the extremisation conditions I told you about in this case reduce to an Attractor mechanism for in ADS for the near horizon data. And even though I didn't say that because I'm more focused on deep story, but there is extremalization principle in 4 dimensions. And exactly this extremalization of the superpotential describes this corresponding extremalization principle in 4 dimensions. I will give it now in 5 dimensions. I hope I can do that more concrete. So the STU model there contains a gravity multiplet and 2 vector multiplets. So two gauges and 3 real scalars, 2 real scalars, but which is more convenient to pack them in these sections that satisfy constraint. Solutions in this theory actually, from a high dimensional point of view, correspond black holes correspond to rotating E3 branes in type 2b supergravity, which you know is dual to n equals 4 super Young Mills. And we expect the entropy to scale like the number of colors squared. The ansatz for these black holes has this form here that I showed also in the beginning. So it can be rotating. Actually, it has to be rotating. But despite that, the problem is one-dimensional because the theta dependence is fixed completely in this sector, in the SU2 cross U1 sector. So what is superpotential in this case? Again, it turns out that it's more easily, I mean, the variables that there are in the 5-dimensional theory are not the natural ones to describe the superpotential, but you have to combine the magnetic parts with the scalars, this combination, holomorphic combination. And in that case, the superpotential is again the modulus of the holomorphic part of the the modulus of a function which is holomorphic with respect to these variables, complex variables. And it's also homogeneous with respect to the parameter h, which, if you recall, it says Gaussian parameter. It's kind of the interval. This is very analogous to the Dallaka-Damiani superpotential for static ionic black holes in 4 dimensions. But it's the first one for rotating ones. Okay, so what's the meaning of Z in that case? So Z, the holomorphic superpotential, is related to the projection of the Killing spinor action. And the modulus, as we said, is the superpotential itself, but the phase is also important. And actually is related to the preservation of some other integrals, 4 supersymmetric integrals along the radial flow. Which are these ones? Okay, the explicit expression are not very important, but they have a very nice thermodynamic interpretation, these supersymmetric integrals. And actually the fact that the chemical potentials of supersymmetric black holes are frozen to specific values. Maybe an analogy would help that the temperature in supersymmetric black holes also is always 0, which we consider as a chemical potential. The same is holds for the other chemical potentials. Any question here? Okay. Besides the thermodynamics, the superpotential is useful for a whole other bunch of things. One of the things is about the asymptotic. So I have the superpotential now exactly, so I can try to solve the flow equations. This might be hard, and the purpose is not to solve them, but one can try to solve them asymptotically, close to the boundary. So you would expect, in general, that if you have the superpotential, you will get some just integration constants that are unrelated for a generic black hole. However, when you have supersymmetry, what turns out, it turns out that these integration constants are related, are not really them. And that's natural, related in this way. So, for example, the magnetic part of the graviphoton is related to the Gaussian parameter of the boundary, and the magnetic part of the vector multiplets are related to scalar sources. And these are exactly the conditions you get if you try to put your theory, your supersymmetric theory on a curved manifold. So you get from here. From the BPS superpotential, you can also compute the renormalized one-mode functions, of course, and it's the Onsel action actually. And since you compute also the chemical potentials, you can verify that these also satisfy the BPS relation. Note that we have done that without knowing the solution at all. And yeah, I have verified that, the Casimir part here comes from the anomalous transformation of the supercarrier of the boundary. Considered as an anomaly of the supercarrier. About attractors, okay, so the superpotential, I stressed that already, describes all supersymmetric solutions, even pathological black holes. In order to get the regular ones, we need to take into account the extremisation conditions. And in that case, when you have supersymmetry, the extremisation conditions amount to extremizing not the real superpotential, but also the holomorphic part. And you can do this, so then all the near horizon data, so note that these are algebraic equations for the near horizon data. So you can solve them. And this is a manifestation of the attractor mechanism. That you can get all your, okay, here, I don't know how, it's different than the attractor mechanism in flat space. In flat space, you have moduli. So here they are only fixed in some sense. But what I'm trying to say is that the near horizon data are determined in terms of the charges solely, and also the entropy. And it gets this form, the entropy, which I don't ask you to remember that, but it's exactly the expression for the entropy that I showed you without knowing the solution. In fact, and question about the constraint, yeah, you get that this system of algebraic equations, the attractor equations, is an open constraint system. And you get from there an extra constraint, which is exactly the one I showed you. So I want to say that this way. Okay, so we know that these are BPS regular real solutions, so they are necessarily extreme. We are still not going to shell as much as we want in this case. How do you make sense of the on-cell action? If you take the constant discarrelation, you see that there is a 0 over 0 in that case. So because of the BPS relation, and because you have an overall beta factor. So in order to compute the on-cell action, actually depends on how you approach the BPS locus. It turns out that the right way to do it, in order to produce a theory result, is going to form examples. In our formalism, this is quite trivial to do. What you do is you consider that your holomorphic variables now are not exactly now are not the one complex conjugate of each of the other. You consider them independent. So the superpotential then takes the same form, but again consider the holomorphic and the anti-holomorphic is independent variables. So intuitively, what this does is that the superpotential, each factor, so you can have one of the factors vanishing, but not the other. So you have a slower blackening behavior, and so this is that's an extremal. And now the attractor equations are just in terms of the one set of variables, not the both of them. And the fact that now your phase of the superpotential has a non-trivial imaginary part results in a non-zero but complex temperature. So schematically, if you want to think, what you would do in Alassane would be to go to extremal solutions, which are not necessarily supersymmetric, and move towards the real BPS locus. But this does not preserve supersymmetry manifest. This process, what instead does, is that we go to black holes which are supersymmetric in the sense that the Killing spinor equation is satisfied formally, and move along this direction towards becoming real solutions, towards obtaining a real solution. The temperature is not zero, so one of the chemical potentials is unfrozen. The same happens for the other chemical potentials in that case. They are unfrozen in a kind of trivial way, in a sense that it's only linear in the temperature. And the deviations from their frozen values are the BPS chemical potential, actually, which if you solve the near horizon equations, you get that specific values for those, and you see that they satisfy the constraint. This constraint was exactly the one that in the beginning in the extremisation process you had to take into account. The BPS relation now is also modified linearly in the temperature. And in fact, this means that now you can get the final value for the Onsen action. And yeah, you get this relation, which sometimes people refer to as the supersymmetric statistical relation. And you see that the entropy here is just, in order to compute the Onsen action, you have to compute the entropy, but you have the attractor equation, so you can compute the entropy, and you get the value for the Onsen action. You get exactly this value, which, if you forget this part, which is for statistical locally solutions, you get exactly in the SU2-1 sector, the entropy functional that reproduces the entropy. So it is exactly the HHG entropy function. And by construction, it reproduces the correct black hole entropy, which is expected. I mean, this is, we have gone off-shell, but in a trivial way. I mean, the same equations are satisfied, but in the complex plane. But we can formulate this and make the analogy more concrete with sense entropy function. So, taking my near horizon data and trading there with the chemical potentials, but without imposing the attractor equations, I can define a superpotential, which is exactly the BPS superpotential, but expressed in terms of the chemical potentials. And from that, I can get an entropy function. And if you do that explicitly, you get that this entropy function is exactly the one that Zaffaroni and collaborators had conjectured, including the Lagrange multiplier that imposes the constraint among the chemical potentials. So it's very similar in a sense to Sen, with the temperature now, the complex temperature, acting as effectively as the ABS2 radial coordinate. So yeah, I mean, again, as in the case with Sen, the extremisation of the superpotential, the conditions I wrote, in the case of the complex BPS saddle, reproduce the entropy function of Zaffaroni et al., which is the correct entropy function to reproduce the entropy of black holes in the field theory.
Is there any further criterion of which complex BPS saddles take, or you have to take all of them, or exactly? I mean, is it a posteriori verified? You just check something or something
In the field theory, or?
well, even in the part, right? This process, I mean, is the whole process that you described verified a posteriori, or a priori you have some sort of principle? This is what I didn't understand. But perhaps the question doesn't make sense.
No,
Posteriori.
Absolutely one.
Yeah,
so if I'm trying to understand correctly, you say there is a specific complex saddle here. If I have a specific value for the temperature, right?
So it's a unique.
No, I mean it's for every value. But it's not real. Sorry. So you see here, I have not imposed. No, where is that? I have not written that. I have to understand the question. Okay. But the formal, the expression gets for the entropy goes for every complex saddle. But it becomes complex entropy. So I'm not sure if you wasn't that correct. If you restrict to reals, you get the correct entropy. The charges are complex as well. Okay, we can discuss. So yeah, I hope I convey the message that with a superpotential, it's possible to analyze problems with large amount of symmetry. So effectively, the problem becomes one-dimensional, and you can say a lot about the thermodynamics without having a solution at hand at all. As a technical result, we got the superpotential, the exact superpotential for a quarter BPS, quarter in the sense of n equals 2 supergravity in 5 dimensions, and which is the first example of superpotential for rotating black holes. And the superpotential provides, the extremization of the superpotential provides a unified entropy function for in terms of those that they exist in the literature, at least. So when you have extremal black holes, it reduces to sense extremization. And when you have complex samples, it reduces to the extremization that people use in the localization techniques. So in the Zaffaroni et al. In 5 dimensions. And also showed that the supersymmetry, the BPS relation is very generic, as it should actually, because of the algebra, even for asymptotic and local backgrounds. And there are a couple of things to work on. I think that's the most important part of the talk. So you might ask, okay, in supersymmetry, we know ways to do things. So I mean, why it is useful? So one thing that is very worth investigating more is to try to find a superpotential for non-supersymmetric black holes. We did for Hosseini-Hristov-Zaffaroni, but you might say that this is trivial. So, for example, for Kerr black holes, what's the superpotential? We tried a bit, we didn't manage to do it, but this would be important. Another thing is that the fact that we consider one-dimensional effective problems is for technical reasons useful, but it need not be conceptually. So if you had not so much symmetry, you would have to talk about an effective action, not an effective potential. So and the Hamilton would be a function of potential. So technically it's harder, but you can do it. And in this, we have black holes in this model that are analytically known, complicated, but they are. We didn't need to use a solution. So the power of our technique would be more visible when the solutions in different theories are just numerically known or easily known. And it's something we are trying to work on. And the other is that is there a high dimensional connection with the superpotential? For example, we are talking about black spheres, and they are defining a different entropy function, which has to do with some extremization on the internal manifold. So I believe that it's connected, our extremization to that one. How do we see uniqueness results in our formalism? Maybe it helps in the classification problem overall that I told you it's very hard to talk about. And the better understanding, I mean, there is all the people cheat a bit here because when they are considering complex saddles, because I mean, how is it expressed in terms of the algebra? What can you say about the unitarity? These are questions that are swept under the carpet when we talk about complex saddles. Thank you.
Any further questions? Who is Black Spinor?
It is. There are solutions that have conical singularities, let's say, on the internal sphere or something that, from the lower dimensional point of view, they are irregular. But when you uplift them in higher dimension, they will be irregular. Yes.
Is there no other questions? Again. I guess this is technically a group. So we can do that.